and then you find the eigenspace corresponding to it, and too bad, the eigenspace has dimension 1. Shannon.
Got it.
Aaron.
What would happen if you had one, like if the eigenspace had 2 and then like, or if it had 2 with the geometric multiplicity, or the algebraic multiplicity of 2, and then another eigenvalue with just multiplicity 1?
Yeah. So in that case, so suppose you have you've got 2 guys, and maybe this guy has algebraic multiplicity. This guy has algebraic multiplicity 2. This guy has algebraic multiplicity 1. Maybe this guy has geometric multiplicity 1. Right? That's what you're saying. Right? In that case, we're basically back in the case that we had before. Right? And our Jordan form will look like number 1, number 1, 1, number 2, like that. Right? And then when you exponentiate it, when you take x of this times t, right, then it basically turns into e to the lambda 1 t, e to the lambda 1 t, e to the lambda 1 t, e to the lambda 2, e to the lambda 2 t. Right? And then you would hit this thing with t to get back to your original. So that sort of falls into the previous case. Okay. I'm going to erase this. Sorry. I'll go first. So, okay, so this thing has algebraic multiplicity, but geometric multiplicity is only 1, and so you're trying to find a generalized eigenvector, and so you say, well, we look at a minus 2I eta equals c. Okay, so geometric multiplicity 1 with the 2 being the span of 0, 1, -1. So, yeah, this first part is just as we've done before. You find the eigenvalue and then find the eigenspace corresponding. So we get one eigenvector, right? And that's all we can get. Okay, and then you just say, okay, well, I'm going to need some generalized. I'm going to need a generalized eigenvector chain. So let's look for the first time, right? You say let this equal to 0, 1, -1, right? And then you solve it, and hopefully, if I did it correctly this morning, then it turns out that eta being 1, 1, 0 will do. Actually, you get a whole bunch of them, with some constant involved, and I'm just setting the constant equal to 0, and you get here's one of them. Okay, and then you do the same thing, right? A minus 2I zeta, set that equal to the to eta, right? Because we wanted the next guy in the chain, right? And we get zeta as 2, 3, 0.
So that squiggly thing is different than C.
It's different from the other squiggly thing. It's got more squiggles.
Really?
C and zeta.
Those are different.
Those are different. Sorry. This is the z. This is the predecessor of z. This is the predecessor of x.
So what's the predecessor of S?
Sigma. AKA capital S, sigma. Right? That's like some sigma, summation.
Standard deviation.
Strangulation.
Standard deviation.
Oh, standard deviation. You see, I'm not into statistics, but I'm clearly into murder. Yes.
For this, did you just solve it using?
I just solved it
Gaussian
Gaussian
introduction?
introduction.
Okay.
Very boring. Okay, so, okay, and then from there, like, what do? Well, you create T, right? You use these guys to create a change of basis matrix, right? Use these guys to create a change of basis matrix, and then you change the basis, right? And you know what you're gonna get. And it looks like this: 2 is down the diagonal, and as long as we construct this properly, then this is what it's going to look like.
Is that T prime or T negative 1?
T negative 1. Conjugating A by the chain basis matrix. Right? And then use exponentiation, right? So then x of jt solves, right, y prime equals jy. So y prime equals ty. And so you exponentiate this guy, and you exponentiate this guy, x jt, turns out to be e to the 2t, e to the 2t, e to the 2t, t e to the 2t, t e to the 2t, and then you get t squared over 2 e to the 2t. Okay, so this is the fundamental matrix for this, right? Fundamental matrix for this, right? And then, right, you get the fundamental matrix for your original system by multiplying this thing by t, right? So Tx jt is the fundamental matrix for x prime equals ax. So you end up with fundamental matrix being 0 e to the 2t minus e to the 2t, right? E to the 2t, t e to the 2t plus 2 plus e to the 2t, negative e to the 2t, t e to the 2t plus 2e to the 2t, t squared over 2 e to the 2t plus t e to the 2t plus e to the 2t, negative t squared over 2 e to the 2t. Right? And so that is your fundamental matrix, and the columns are the columns are the solutions.
For this, did you know that there were only going to be 3, like a chain of 3 because it's a 3 by 3?
Yeah, it's not going to go on.
Okay, so if you had like, I mean, we probably won't do it, but if you had like 4 by 4, there would be 4. Or are we just think of it as like 2 will have 2?
Well, something funny could actually happen. Okay, so you could have, it could be, say that, so I didn't want to get into this, but I should actually tell you what actually happens. Right? It could be that you have like, you could have like an eigenvector of algebraic multiplicity 4, right? But geometric multiplicity 2. Okay. And in that case, when you try to construct the eigenvector chains, well, there are a couple of possibilities. It could be that, right, you've got C1 and you've got C2. And you've got two good eigenvectors to start off with. And it could be that this guy leads to a chain of 3, and this guy doesn't lead to a chain. Or it could be that each of them leads to a chain of 2. Right? And so your Jordan form will depend on what happens when you try to construct the eigenvector chain. Right? It could be that your Jordan form looks like looks like this, right? This would be, each one has a chain of 2, right? Or it could be that, right, one has a chain of 3 and the other doesn't have a chain, right? That could happen also, right? And depending on the Jordan form, and there's a way of figuring out what's going to happen, but I'm not going to tell you. Look it up. Look it up on Wikipedia if you like. Depending on what happens, then these solutions will depend on which of these options occurs. Yeah. Kevin?
I have a question about finding the top right number in the xjt. Is that always going to be t squared over over lambda e to the lambda g? Or
It's a homework problem. It's a homework problem. We'll leave it.
Okay.
It's not hard. It's not hard. They give you most of it. They give you most of it. Kristen?
Can you really quickly remind me why we go from t inverse at to the exponent of t?
Because you do the change of variable thing.
Okay.
Right? You do the change of variable of y equals t inverse x. And then your system becomes 1 times equals j y. Right? And
And then
from
we
there,
know that
that it's solved by the exponential function.